You want to learn about buoyancy? I want to talk about buoyancy. So let's see what you can do with it. Let's make it easy. So to understand buoyant force and buoyancy, we need some basic arrangements. This is my beaker. It is made of glass. This is a glass cup. And I have pasted the milliliter scale on it. How did I do it? I will tell you in the later part of the video. Okay. Now I need a ball and the color liquid. So you can say, okay, sir, you made the same arrangements that I have seen in the other YouTube videos. What is different here? So for that, I must tell you, bear with me, the discussion can be somewhat different and I will try to make it for you. So I must tell you one thing, all the basic principles of this buoyant force and buoyancy is written in the Archimedes principle. So that principle will be our guide. Okay. Well, if I put this ball on the liquid inside this beaker and go on in a discussion guided by the Archimedes principle, there can be two parts of this discussion. Number one, the upward force applied by this liquid on this object, on this ball. And the second part is the magnitude of this force. We save this second part of this principle for discussion for the later part of the video. Now start with the first part, the upward force. So as the ball rests on this liquid, or if I try to push this ball down into the liquid, try to sink it, the liquid applies an upward force on the ball. This force is known as the buoyant force, and the property of this liquid is buoyancy. But wait, how do I know the force is applied in the upward direction? How do we know the direction of this force? Well, I can give you some ways to understand the force is upward. Number one way is the feeling. I can feel the upward force on my fingers. Well, I cannot show you my feelings. For that thing, you have to trust me throughout this video that the liquid in reality is applying a force on my fingers through this ball. You can try it out in your place by yourself. There are other ways to understand the existence of this upward force. The next way is through measurement. Let us see how we can measure and understand the existence of this force. For this, we need a spring balance. I have my own digital spring balance for this, and we need an object like this. I need this heavy object so that it can sink into this liquid without my help. Let's switch on the meter. So the weight of this load is 65.065 kg. This kg means a kilogram force, not the mass. Let's dip it. So you can see it is 0.40 kilogram. Now let's come to our on-board discussion. So that was our container, somewhat, pardon for my drawing. That was our liquid. That was the graduation. And so when the ball was outside, like here, its weight was 0.065 kg, and I said you that this is not just kg, this is kg weight or kg force, you can say. So you have to multiply this with acceleration due to gravity to get the weight, actual weight in Newton. Now when I dipped it inside the liquid, this time, this thing, if it goes into the liquid, its weight was like 0.040, that kg weight. So you can clearly see this difference. So as we know, the weight of the body acts directly vertically downwards towards the earth, toward the direction of gravity. So previously outside the liquid, this was its weight. So when we dipped it inside the liquid, its weight goes to 0.40. So there is a clear decrease of weight, As this decrease in weight is in the vertical direction, so obviously the upward force, the opposite force, is in the vertical direction and opposite to the direction of the acting actual weight. So this is how by the method of measurement we can understand that there is a clear upward force on this ball by the liquid. So let us recapitulate very quickly whatever we have studied so far. So first of all, we have understood the concept of buoyancy, whatever it is, and the buoyant force. We have understood that all the concepts of buoyancy are pinned inside Archimedes' principle. We have understood that there are two parts of the Archimedes principle. One is related to the upward force applied by the fluid onto the object, whatever is dipped partially or fully inside that fluid, and the second part is the measurement of that force. We haven't yet discussed the measurement part, the measurement of this force. To understand the existence of upward force, there are few methods I can share with you. The first method was to understand it through feelings. For this part you have to do it on yourself, or you have to trust me that the force is applied on my fingers. The second understanding came through measurement. So this measurement is not related to this measurement. This measurement is another way of measurement how Archimedes has designed in his principle, but this measurement is through spring balance, whatever we have done. The third part of understanding, the third way of understanding the existence of this upward force is through correlation. We can correlate of our previous understanding of Newton's laws, specifically Newton's second law of motion, to have an understanding the force is in the upward direction. So let us discuss this third thing, the third point of understanding. So let us get back to our main discussion. So a third way of understanding of the upward force by the liquid on the object is a correlation. Correlation with the Newton's second law. So see what I am doing. If I press this ball all the way down inside the liquid, now the velocity of the liquid is 0 meters per second. But if I release it, it makes its way all the way up to the surface of the liquid with a gaining velocity. It gains velocity if I release it. So Newton's second law says what? The change of momentum takes place in the direction of the applied force. Here the momentum or the velocity changes in the upward direction. So obviously there is a net force acting upwards, which is our buoyant force. So welcome to the second part of the video, that is the measurement of the buoyant force. For that we'll need the same object we used few minutes back. Remember this one? We will use this object to understand the second part of the Archimedes principle, that is the applied buoyant force is equal to the weight of the displaced liquid. So before putting the object inside the liquid, let us check that the upper level of the water is at the mark of 85 milliliter. Now let us put the object, that glass bob, inside the liquid. So we put it. The water level comes up to 110 milliliter. In the third condition of our understanding about the upward force, we measured the weight of the bob inside the liquid and outside the liquid. Outside the liquid is weight was like this, 0.065 kilogram weight, and inside its weight was like 0.040 kilogram weight. So the difference was like 0.025 kilogram weight. Let us see if we can verify this weight difference through our immediately last experiment, whatever we have done. So let us see if we can verify this weight difference with the help of whatever we did lastly. So the final water level minus initial water level, that is the water displaced by the whole of the object by dipping inside the liquid. The final water level was 110 and the initial water level was 85 that ml. So you can see there is a 25 ml of liquid, and to get its equivalent meter cube volume you have to multiply this factor with 10 to the power of minus 6. You get the meter cube. Now if I want to have an equivalent mass of this volume of liquid, I have to again multiply this factor with 10 cube, 1000. You can guess this, you can get these conversion factors on net. I won't spend much time on this bookish data based information. I'm just here to make you understand the concept and discuss with you. So by multiplying that thing, you are getting a mass of 0.025 of kilogram. So this mass of liquid getting displaced, obviously the weight of the of this mass of water would be 0.025 kilogram weight, which is exactly equal to whatever we have measured in the third part of our understanding about the upward force. So you can see there are three ways to understand there is an upward force, and you can verify the second part of the Archimedes principle with the help of this very small and low cost experiment. So let us get back to our video. So let us see how can we do it. How can we draw a perfect or nearly perfect a milliliter scale onto this irregular shaped container, and obviously it has to be transparent. So for that I have taken my container, and for help I need a 60 ml syringe. You can do it with any kind of syringe, the larger the better. And also I have taken some colored liquid so that you can see it. So what I have to do, I have to fill this syringe full up to 60 ml. So let's do it. So as you can see, I have filled with red colored liquid into my syringe. So what I have to do, I will eject 5 ml of liquid onto it into this cup, exactly 5 ml by my syringe, and mark that level with a marker. So I mark this level here. I eject another 5 ml into my cup, and mark it as well. So as you can see, at every 5 ml liquid into the cup, I have given a mark with my CD marker, and I will do it twice to make it a 120 ml beaker. So here I have done it, my 120 ml of markings, and now I will get rid of the water and give these lines a level, like 0 markings to 120 ml markings. And now you see a well graduated milliliter beaker. Okay, so the question comes, are these markings are equally spaced? Well, obviously no. Why? Because this container is irregularly shaped. And now the second question comes, the process I followed, was this a perfect one? Well, obviously no. There are errors in the measurements. As Professor Walter Lewin of MIT, he was a very good professor in there, he always said that any measurement without the understanding of errors is meaningless. So what are the errors? What can be the types of errors I can get? One of the major errors is, whenever I was drawing these markings, I can have an eye level problem, because you have to see very much horizontally through that level. So there can be an error of that. The second kind of error that can be introduced into it, that whenever I was injecting in liquids in this syringe, there can be air bubbles. So there can be a volumetric problem in here. The volume I saw as 0 level may not be 0 in actual. There can be errors due to air bubbles in this syringe. And the third kind of error that can arise is due to the surface tension of the liquid itself, because the edge where the liquid touches the wall of the container is not a perfectly horizontal one. There is a curvature due to the surface tension of the liquid. So this is it. So this is the very last part of the video. I will close this video after telling you this. I can't end this video without sharing this bit of history with you. This guy over here, he is Archimedes. He was born nearly 287 BC. This was the year he was born as per records. And this guy over here, everybody knows him. He is the Newton. He was born in the year of 1643. This is AD. So you can clearly see at this year, Archimedes never had Newton's second law, first law, third law, whatever laws Newton has discovered. So as we have the laws of motion, laws of gravity. Archimedes didn't have those things. He didn't have the definition for force what we have today. He never had the idea of measurement of force as we measure it from the Newton's second law. But at that period of time also, he had the idea of force, its direction, all by himself, by measurements, by feelings, or whatever observation he has made in past. So you can clearly see how tough it was for him to come up with an idea like Archimedes' principle. So guys, this is how science works. No matter how much credit we give Newton for discovering all those laws, the path of these discoveries or inventions were made easy by the discoveries what was done before. This is how science propagates. This is how science works. There is not any particular point in history which is not helped by the inventions and discoveries and thoughts which were done in the past. Thank you for all your time you were with me throughout this video. Thank you for all your patience. In the next video we'll discuss about Pascal's law. Till then, goodbye.